Hello everyone, welcome back to our Calculus 2 course this semester. In this clip, I'll be talking about the very last section of our course. Yes, this 11.10 is about the Taylor series and the Maclaurin series. Okay, so let me put it down on the board. Where's my marker? 11.10 Taylor and Maclaurin. Let me make sure that I spell Maclaurin right. Yes, Maclaurin series. So, what is it all about? In the previous two sections, we've been talking about some type of function, some special function, such that 1 over 1 minus x, 1 over 1 plus x, tangent inverse of x, or etc. ln of x plus 1 or 1 plus x, those kind of function can be represented as power series. Okay, so in this section, 11.10, we're gonna try to learn in a more general case. We're gonna try to answer the question such as what kind of function can we represent as a power series? And let me just give you an answer ahead of time. The type of function can be represented as a power series called analytic function. So for this level, analytic function means that the function you can take derivative forever. Okay, make it easy that way. And if the function can be represented as a power series, the more serious question is, can we actually find the power series of that function? Okay. So this is how the work starts. Say you have a function f of x, and if you believe that that function can be represented as a power series, let's find out the power series of that function. So assuming I have a function f of x can be represented as a power series, say c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus c4 x minus a to the 4 plus da 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 da. So you see this is the power series center at a, right? And say the radius of conversion is r, so x minus a is less than r. Could be equal at the end point, but I'm gonna make it that way first. Okay, so if you have a power series, you have a function, and you believe that's a function can be represented as a power series. Of course, a is a constant, you know, right? Center at a. So in a nutshell, your job is to look for all the coefficients. If you can find all the coefficients, then you know the presentation as a power series of that function. Okay, so let's try to figure out all C. How do we find it? So say you plug in x equal to a, I'm gonna look for C0. Okay, if I plug in x equal to a, I got what? F of a, okay, is equal to, well, this is 0, 0, 0, 0, so this is just C0. So I can find the first term right away. So C0 is f of a. Alright? Now, I got the first term. What I'm going to do now is f prime of x. Let's see, talk about analytic function. Keep taking derivative, right? So if function, you can take derivative forever, then this is not a problem. If you take derivative of f, you got f prime of x. And what is f prime? You got a power series right here, derivative constant is 0. It's going to be what? C1, derivative this, right? Plus 2c2 x minus a plus 3c3 x minus a squared plus 4c4 x minus a cubed plus dot dot dot. You have f of x, of course you can find the derivative. Okay? I don't know the power series yet, but I know the function. I can find the derivative. And we learned before it's a function can be written as a power series. Its derivative gonna be able to be written as this power series. And now I plug in x equal to a again. Then I got f prime of a. All the terms right here are going to be 0. Then it's going to be c1. You see the strategy? So I have a function, and I know that if the function I can take the derivative forever, then I can find the first term I list and the second term. Okay, I list the first term and the second term. Keep going. I will calculate the second derivative. Then this cancels out, right? So this is what? 2c2 plus 3 times 2 c3 x minus a C2, I forgot x minus a for C2. 2c2 Oh, there's no x minus a. Right. Okay. And then what? Plus 4 times 3 C4 x minus a squared, blah, blah, blah. Now I can calculate C2. I'm going to plug the next equal to a again. And I got f double prime of a is equal to 2C2. Right? Because all the terms from here all the way to the right will be 0, except for the first term. So I can calculate C2 from here. C2 is f double prime of a over 2. Divide both sides by 2, we got C2. Okay. Then same thing, f triple prime of x. I have what? This is 0, so what? 3 times 2 C3 plus 4 times 3 times 2 C4 plus da da da. You see what? This is actually what? 4 factorial. This is 3 factorial. Okay. C4. I forgot the factor right here. And what? X minus a, and then the next step going to be what? 5 times 4 times 3 times 2 x minus a squared. Next step going to be 6 times 4 times 5 times 4 times 3 times 2 x minus a cubed. Keep going. And of course I do the same thing. I plug the next equal to a. I got third derivative at a is equal to 3 times 2 right here. I write it as 3 factorial C3, and that's helped me to calculate C3. C3 is equal to f third derivative of a and then over 3 factorial. And by induction, we learn induction in the pre-calc, okay? So similarly, keep going. You're gonna see what? Cn is gonna be equal to f derivative n time at a and then divided by n factorial. Okay. And let me box that this is one of the important formulas about Taylor series. This we need to know. Right? So, if you have a function, and this function is an analytical, a function that you can take the derivative forever, then you can say that I can find a power series for that function. Okay, and the power series can be written that way, where Cn is equal to derivative n times at a and divided by n factorial. Or combine them together, you guys can write it this way. F of x is equal to sum of Cn x minus a to the n run from 0 to infinity. And this is actually equal to sum of fn a over n factorial of x minus a to the n with n run from 0 to infinity. Same thing, I just replace Cn by that. This is exactly what we have up here. If I unpack the package, I got this. C0, C1, x minus a to the first, C2, x minus a to the second, C3, x minus a to the third, plus that. And of course, Cn is replaced by that thing. So C0 is f of a, right? C1 is f prime of a over 1 factorial, x minus a, C2 is f double prime at a over 2 factorial, x minus a squared, C3 is f triple prime of a over 3 factorial, x minus a cubed, and plus that. And that is the main idea about the Taylor series. So what is a Maclaurin series? And I glance actually you learn about Taylor series, you know everything about Maclaurin, because what? Maclaurin series is a very special type of Taylor series when that a right here is equal to 0. At a equal to 0, then what do you have? Well, replace a equals 0 right here. Then you have what? F of x is equal to the sum of what? Fn to the 0 over n factorial times x to the n. N run from 0 to infinity. So replace a by 0. That's all you have to do. So this is what? F of 0 plus f prime of 0 over 1 times x plus f double prime of 0 over 2 factorial x squared f triple prime at 0 over 3 factorial x cubed plus dot dot. Okay? Of course, Taylor series is going to be more powerful because not all of the function you can plug in 0. You can find the center at 0. You can plug in say f of 0. You cannot calculate f of 0 as some type of function. For example, ln of x. You cannot have ln of 0. Okay. In other words, you cannot find a function center at 0. Then you can find center at other point. So Taylor series is a more general version of the Maclaurin series. Okay. I think at that time people have lacking of ability to communicate with each other. So Taylor do his own work, Maclaurin do his own work at different places, and there's no internet to communicate, so they don't know each other works. That's why we honor most guys. And I think that's Newton, Sir Isaac Newton worked on this too, and many other people like Bernoulli worked on this stuff too. So make sure that you check for it, okay? I say something, I'm not 100% sure about those, but that's what I know. So you can double check on my work on that. Okay, but this is the idea of Taylor series. You say what? You have a function. If you can take the derivative of the function forever, then for sure that function can be represented as a power series. And center at some fixed number a, okay? Any number that you choose right here, that's what Taylor said. And all you have to do is find the coefficients. The C number is right here. And the formula is Cn is f, n derivative at the center a divided by n factorial. That's the whole thing. So let me give you an example. I'm going to give you a couple examples. Okay? And you see the idea. So let's start the example I like the best. This is a function. F of x equal to e to the x. And I gave you the example of this one on the previous section. But I gave you the power series. Now we're going to find the term in that. Let me just write it down. This is going to be equal to what? 1 plus x squared over 2 factorial, x cubed over 3 factorial plus dot. Okay? Whatever. This is what you know. But now, assuming that you don't know this, how can you figure that thing out? How can you figure out the power series? We're going to do it step by step. Okay? So if we don't know this, we're going to figure it out. So I'm going to use Maclaurin series right here. Means what? Center at 0. Easy, right? 0. You can plug an x equals 0 in here easily. So I'm going to use Maclaurin series. I'm going to have this is C0 plus C1 x plus C2 x squared plus C3 x cubed plus C4 x to the 4th C5 x to the 5th plus dot dot. And my job now is to find out all the C's. C1, C2, C3, C0, all of them. See, center at 0 is what? X minus 0, x minus 0 squared, so I don't have to write minus 0. The center is at 0. Okay, so let's start with C0. How do I find C0? I'm looking x equal to 0 and center at 0. I got what? F of 0 is e to the 0 is equal to C0. F of 0, x equals 0, c to the 0, right? All those terms right here equal to 0 to the first term, which is equal to 1. Okay? And remember, that's e to the x that I gave you before, 1 plus x squared over 2 factorial, x cubed over 3 factorial, and 4 over 4 factorial plus 1. See if we're going to get to there. So first one right here, 1. Good. Now, I'm going to take the derivative of this. F prime of x is equal to e to the x. Okay? So f prime of 0 is equal to 0, right? So what is f prime of 0? F prime of x is still equal to e to x. So let me just write the whole thing down first. This is what? C1 plus 2c2x plus 3c3 x squared plus da da da. Okay? And I plug in what? X equal to 0 in here. So f prime of 0 is equal to e to the 0, which is equal to c1 equal to 1. So I got c1 equal to 1. Okay? So you see the formula actually apply. And we call the formula Cn was fn to the x over n factorial, right? I can have C0 already, C1 already. I can calculate C2. C2 is f second derivative of 0. This is A. over 2 factorial. You see that e to the x, the derivative is always e to the x, so it's always e to the 0 over 2 factorial. This is 1 over 2 factorial. Okay. Similarly, 3 to the 4th, so Cn is fn derivative at 0 over n factorial, which is 1 over n factorial. See? 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. All the Cn is that you have the power series for E. Okay, so let me write in here. Over 2 factorial, over 3 factorial, over 4 factorial, over 5 factorial, plus that. Okay, 1. This is your power series for the E function. Okay, so calculate f prime. See what you got? It's e to the x, right? Really, is that e to the x? The derivative of 1 is 0. The derivative of x is 1. The derivative of this is what? 2x over 2 factorial. You see the 2 cancel out, so it's f, right? This is what? 3x squared over factorial. 3 factorial, 4x cubed over 4 factorial, 5x to the 4th, I mean, over 5 factorial plus, you see what? This is just 1 plus x squared over 2 factorial because the 3 cancel out. This is x cubed over 3 factorial, x to the 4 over 4 factorial plus, so the derivative about the same. Okay, try another one. Some function that we can take the derivative forever. How about f of x? Let me get another marker. F of x equal to, say, cosine x. Equal cosine x. All right. So you know that Cn is this. So to calculate what? F of 1 and calculate C1. How do we write it? F of x is cosine x. So center at 0. Okay, make it easy. My Lorentz series. So x equal to 0. F of 0 is equal to cosine of 0. Cosine of 0 is equal to 1. And then C0 is equal to f of 0, which is 1. Okay? So f prime of x is equal to the derivative of cosine is negative sine x. So f prime of 0 is equal to sine of 0 is 0. So C1 is equal to 0 because C1 is f prime of 0 over 1 factorial. Then f double prime of x, the derivative of sine is cosine, so negative cosine of x. So f double prime of 0 is equal to negative 1. So C2 is what? F double prime of 0. F double prime of 0 over 2 factorial. This is negative 1 over 2 factorial. Okay. Try one more. F triple prime, third derivative of x. The derivative of cosine is negative sign with a negative is sine of x. Okay. So f triple prime of 0. Derivative sine of 0 is 0. Well, this is 0 already, so C3 is equal to 0. So I'm going to try one more. The fourth derivative of f. So now you see what? 3 apostrophe right here, right? So 4 instead of right 4, right? Number 4 in parentheses. It's getting bigger. The derivative sine, go back to cosine of x, and then derivative 4 times is at 0 is 1. Cosine of 0 is 1. So C4 is f derivative 4 times at 0 divided by 4 factorial. So 1 over 4 factorial. Okay. So keep going. Okay, you can calculate the 5th derivative, the 6th derivative, so forth and so on. So you see what at least for the first couple of terms it's gonna be what? F of x. Let me. Oh, I erase it. Let me rewrite it. C0, C1, x minus a. C2, x minus a squared. C3, x minus a cubed. C4, x minus a to the 4. You have in here what? C0 is 1 plus C1 is 0, so it doesn't matter what it is. 0 plus, this is going to be what? Plus with a minus, so minus. What is that? Minus 1/2 x squared, because A0 center at 0, right? Center is 0. So minus 1/2 squared plus 0, and then 4 right here positive, so plus 1/4 x to the 4 plus that. And so if you simplify, you're going to have something like this. 1 minus 1/2 of x squared plus 1/4 x to the 4 minus 1/6 x to the 6 plus 1/8 x to the 8 and minus 0 and so forth and so on. That is for the cosine function. Cosine of x. Okay. Similarly, you can have the sine of x. You do the same way. You have sine of x going to be x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, 1, 3, 5, 7, and then plus 1/9 x to the 9th. And I think factorial, I forgot. Factorial. Okay? Plus da 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 da. And you can check for the problem see if it's true. You know what? The derivative of sine is cosine, right? The derivative of cosine is negative sine. So let me take the derivative of sine. The derivative of sine x, derivative. See what I got? The derivative of x is 1. The derivative of this is going to be minus 3x squared over 3 factorial plus 5x to the 4 over 5 factorial minus 7x to the 6 over 7 factorial plus 9x to the 8 over 9 factorial plus da. And that simplifies what? 1 minus the 3 again, so you got 2 factorial in the bottom. And this is x squared. Similar is x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial minus s so forth. So this is really cosine. See? Derivative sine and cosine. And similarly, you take the derivative of cosine, you have sine equal to cosine of x. And this is very powerful. Okay. So you see that in this section we can actually use Taylor's and Maclaurin's series as the presentation of a function, of an analytic function. Okay. Next, I'm going to talk about approximation. So pretty much, you can approximate a function using a polynomial. Okay? Of course, with a tail. With some remainder. Say you have an analytic function, and of course there's no way that we're going to calculate all the terms all the time in reality. We're going to use a couple terms, the couple first term to approximate the function, and a couple first term is no more than what? A polynomial. Right? This is really a polynomial. So let me write the general term. Put that all the way to Cn x minus a to the n and then plus more. Okay. If we use n term to approximate the function, this is called Tn of x. This is a polynomial of degree n. Okay? And plus what? Plus some remainder. Okay? This is like the error of your approximation. Okay? And this is what over right. This is our n right here. And I'm writing down here. So in short, you can think of f of x is equal to Tn of x, a polynomial plus a remainder. Okay, this is a polynomial. This is a remainder. This is an error. So in other words, f of x is approximately equal to a polynomial plus a little remainder right there. Okay. And there's a theorem in our book saying that if you can write a function of the form of what? A polynomial, Taylor polynomial, plus a remainder, and with the integral conversion right here, x minus a, I mean, less than r. If you can write it this way, and you know that Rn is going to 0, Sn go to infinity, then you know that this function that's going to be written as a power series. That's a Taylor series. If this happens, if f of x equal to a polynomial plus a remainder, and the remainder is getting